All right, thanks, John. So I'm going to talk about an exciting new part of the web's public key infrastructure called certificate transparency. I'm going to start out by describing certificate transparency, what it is and how it works, and then I'm going to go on to explain some privacy-preserving improvements that we've made for certificate transparency in our group. So this is work that I did with Iran Masseri at Google, Joe Bonneau, and Dan Bonnet in last fall. So to set the stage for the problem we want to solve, we know that every site that our browser wants to visit has some public key, and once it gets the public key to us, the browser is able to establish a secure connection. And the way that we make sure that the public key that our browser gets is an authentic one is we have a certificate authority that acts as a trusted third party. So the idea is that your sites, like Facebook, is going to send its public key over to the certificate authority, the CA, and the CA is going to sign off on this public key and say this is the legitimate public key from Facebook, and that certificate gets sent back to Facebook, who then gives it to your web browser when you go to visit. And your web browser accepts the certificate because it trusts the certificate authority. And this is great. We have a trusted third party that makes sure that all the keys that our browsers are using to connect to these sites are authentic. But it can be problematic if the CA is not as trustworthy as we had hoped it would be. And this is something that happens sometimes. So in particular, in 2011, a number of Gmail users in Iran thought that they were going to Google to check their mail, when in fact they were probably going to their government, who had compromised the CA named Auditor and had issued fake certificates for Gmail. So all of these users thought they were going to Gmail, but in fact they were going to probably their government who did the attack, and were having all of their emails surveilled. So this failure of a CA allowed for mass surveillance, which is not what we want to have happen. This was not a one-time thing. As recently as last year, there were some more CAs that were distrusted by Google because they were also failing in their responsibilities as being a trusted third party. So this kind of led to demand for some sort of mechanism for policing CAs that might be going rogue or might be somehow compromised by attackers. And this is where the idea for certificate transparency came in. So the thinking behind this is that the reason that Google was kind of vulnerable to these kinds of attacks when there was a fake certificate issued is that these attacks kind of happened in the dark. So Google didn't know that there were fake Google certificates being issued until later. But if it did, it would have been able to say, hey, these certificates are bad, browsers should not trust these certificates, we should go punish this CA. But because it didn't know about this until later, it wasn't able to catch the attack early on. So the goal of certificate transparency is, why don't we make a public verifiable log that has every certificate that gets issued on the log. So the idea is that if some CA issues a bad certificate, then Google will know that there are extra certificates for Gmail that it didn't request that are being distributed, and it will know to go and revoke those certificates or to go and punish the CA that issued the certificates. So what we have here is a log that has all the certificates on it, and then any interested stakeholders, be it the CAs or the owners of the different sites, can look at the log and see that either the only certificates that are out there are the legitimate certificates that we wanted, or maybe there's other rogue certificates that we need to handle out there. So the way this stuff gets on the log in certificate transparency is that when you go to the CA to request a certificate, the CA kind of passes the certificate onto the log, and then the log issues a promise that it's going to include this certificate in the log. And this promise is called a signed certificate timestamp. So it's a signature on the certificate that appears in the log, as well as a timestamp of when this certificate was received to be put into the log. And then later it puts the certificate in the log. And then the CA, when it sends Facebook the certificate, it also sends the SCT, so that you have a promise that it's in the log. And then your browser receives both the certificate that it gets right now and also the SCT, so that it knows that this certificate is supposed to be in the log and it's being logged properly. The next question that kind of comes up is, well, we now have this log that shows every certificate that's out there, and everybody can look at the log, but aren't we just kind of pushing this trusted third-party problem one step further? What if the log is malicious? So the way we handle this is the browser can act as an auditor, and it has the ability to say, hey, I have these SCTs that I got while I was browsing the web. Can you prove to me that the certificates that I'm looking at actually appear in the log, and you didn't just lie and not include them after you said you would? And so there's efficient ways that the log can kind of prove that all of the SCTs that you've encountered are actually in the log. I'm not going to go into the details of how it works, but I think it's clear that you can imagine how a log could do this kind of thing. So this is the kind of the very high level overview of how certificate transparency works. And it does a really good job of solving this problem where when you, like a bad certificate is issued, you can kind of go and see, and you'll know when a CA has misbehaved and there's bad certificates out there. The problem that comes up here is actually, oh, I should mention, to show how relevant this is, Google has said that Chrome browsers will require certificate transparency for all sites by October of this year. So this is a technology that's actually in all of our web browsers. It's already used for extended validation certificates, and it's going to be used for every certificate in a few months, which I think is pretty cool. But yeah, so this is a great way of catching CAs that have gone rogue and catching extra certificates that shouldn't be out there. But the problem with giving this really great visibility into the activities of CAs and into what certificates are out there is you kind of get a privacy problem. And this is a problem that I encountered personally in high school. I made myself a backpack out of Scotch tape, and I made myself a matching wallet out of Scotch tape. And it was really cool, and I thought it was great, but then people, every time I took out my wallet, would know exactly how much money I had. Kids in the hallways would start asking me for gum, and I realized that this was not such a good thing for me, because stuff that should have been private and only known to me is now known to everybody. And the same issue exists for companies who have private subdomains that they want to use. And so what happens in CT is every subdomain or every domain is kind of listed on the log. So if Facebook, for example, has some secret project that they're working on at secret.facebook.com, and their browsers all require them to use certificate transparency, now Facebook's secret project is visible on the log for everybody in the world to look at and see. So another example, maybe Apple has like iPhone10.apple.com that they're waiting for the announcement of the iPhone 10 to make public. But if they want to have it ready ahead of time, they can't do this in the certificate transparency setting because everybody gets to see that iPhone10.apple.com exists. So the problem we want to solve is, ideally, we'd have some mechanism for taking this secret domain that has to be logged on the CT logs and redacting the private part. So we could take secret.facebook.com and somehow hide the secret so that what people looking at the log would know is that there's something.facebook.com, but they wouldn't know what exactly that is. So Facebook secrets get to be protected. So the crypto tool that we're going to use to achieve this is called a commitment. And a commitment is kind of the cryptographic equivalent of having like a lockbox. So what you can do is you have some value that you want to commit to, and you put it inside of a commitment, and then you send it over to somebody else, and there's two properties that you want to get out of the commitment. The first property is a hiding property. So this means that the value that you put in the commitment, when someone else is looking at it, they won't be able to tell what the value was. It's hidden, like it's inside the box. The second property is when later you want to decommit, you want to open the box, you send over the opening for the commitment, you can't change your mind and say, you know, I committed to value 1 before, but now I really wish I'd actually committed to value 2, and somehow change it. This is not something you can do because the commitment has the binding property. So just like if you put something physically inside of a box and you can't change it once it's in the box, the same property holds digitally with the commitment, because once something has been committed to, you can't change your mind. So this is what a commitment is, and it's very straightforward how once we have this tool, we can use it to solve the problem of private subdomains that I just mentioned. So what we're going to do is, when a site wants to get a certificate, it sends the CA the same information that it would send before. But now in addition to that information, it also sends a kind of a redacted version of the domain name, where the secret part, instead of being the text secret, is a commitment to the secret part, and then the rest of Facebook.com is as it was before. And also you send over the opening for the commitment to the CA. So what gets sent to the log is going to be a pre-certificate that has the secret in a commitment and then .facebook.com. So that what the log ends up logging is the commitment to the name of the subdomain .facebook.com. So anyone who looks at the log doesn't know what it is that Facebook is hiding on the log. It just knows Facebook has something on the log. And likewise, the STT, this signed promise that this information is included in the log, it only includes this commitment and not the actual plain text of what the subdomain is for. And like at the end, when you get this certificate, what you end up having is the certificate for secret.facebook.com with the SCT that has a redacted subdomain and the opening of that SCT. So when your browser goes to Facebook and requests secret.facebook.com, this would be like some Facebook employee, what they end up getting is the certificate and the SCT and the opening of the SCT, and they can make sure that the SCT that they've got corresponds to secret.facebook.com by verifying the commitment opening. So they open up the commitment, they make sure that they have a commitment to secret.facebook.com, and that the certificate is for secret.facebook.com, everything checks out, and they use the site, and they know they can trust the key. So this is how it works. It's very simple. And there's a couple of security questions. So it's very clear that once you have the commitment on the log, nobody can look at the log and find out what the secret is. But the next question that comes to mind is how can you still monitor the log? How can Facebook look at the log and know if there are extra Facebook certificates out there when everything on the log or many things on the log are now redacted? And the insight here is just that Facebook knows, like if Facebook has 10 private subdomains, there's 10 subdomains on the log, that it knows it's good. But if there's suddenly 11 redacted subdomains on the log, it knows that someone has issued a fake certificate. So it's still able to do this job. Another question that might come up is if you have these redacted subdomains, why can't you reuse them? Because after all that's listed is something hidden.facebook.com. You could come up with some other secret website at Facebook. But the binding property of the commitment prevents this from working out. So that's all I wanted to say about the private subdomains. I hope that you're convinced that this is like an effective and simple solution to a real problem. The next problem that I want to talk about are these deals with the case when a log has misbehaved. So I mentioned earlier that you could, the way that you check that a log is not misbehaving is that your web browser, once it gets all of these SCTs from browsing the web, it can go to the log and say, hey, prove to me that this SCT is included in the log. So the question we have to ask is what happens if the log fails to provide this proof? What if the log had actually promised that it would include some certificates, but then it didn't because it was trying to hide something? And so the way we solve this problem now is if your browser has an SCT that's missing from the log, say for secret.facebook.com, the browser sends the SCT that's missing to some outside authority. So in the case of Chrome, this would be like Google. And then the authority, so Google will look at the log and say, hey, okay, yeah, this SCT does not appear anywhere on the log. The certificate isn't there. So this log must have been lying, and we can go punish the log or take some action. But the problem with this from a privacy perspective is that if the auditor of the log is your web browser, then your web browser is only seeing SCTs from the sites that you visited while you were surfing the web. So in particular, Google will now know that you've gone to these websites that have been excluded from the log. The problem is even worse than this because if the website that you'd visited was a private website, like in this example, it's secret.facebook.com, Google, who would otherwise not know that secret.facebook.com exists, now learns that Facebook has this secret website. So not only are you revealing your own private information, you're actually enabling corporate espionage. So this is something that we want to avoid. So our goal is going to be to provide some mechanism of proving that you have an SCT that's missing from the log, but also not revealing the domain name that's been excluded from the log, not revealing the timestamp, not revealing anything else, only allowing the vendor of the browser to know that there's something missing from the log. This log has cheated. And that once it does that, it can go and it can investigate the log and find out what went wrong. We have an additional kind of tweak to our main protocol that allows the verifier to blindly revoke a missing certificate. So once you have this SCT that's been excluded from the log, you can prove to Google that you have this SCT. Google learns that there's an SCT missing, but doesn't learn what website it corresponds to. And it gets this kind of magical ability to blindly revoke the certificate. So it can push out some information to every Chrome browser that says, hey, there was an SCT that's been that's excluded from the log. We're investigating the log. In the meantime, if you get some SCT, you can run this check on it, and you'll know that you've encountered the bad SCT. But we don't know what the bad SCT is, which I think is a pretty cool property to have. So this is what we're going to construct. So the first thing we want to think about when we want to prove this is we need to think what exactly is it that we want to prove. Because when we're in the setting, when you send the SCT over, Google can look at it and it learns everything about it and it goes and it looks in the log. But if we want to do some statement, prove some statement of the form we have an SCT that's missing, but we don't want you to know what it is, we need to think about what exactly is it about the SCT that you're sending to Google that allows Google to learn that this SCT is not in the log. So in principle, there's a number of ways that Google could learn that an SCT is missing. It could go to the log and it could look at each entry and it could see that the entry doesn't correspond to the SCT that it's looking at, and then it will know that if every entry isn't that entry, then it's missing from the log. But we want to come up with a set of conditions that are kind of minimal, so that the work that the verifier has to do is very little to learn that something is missing from the log. And that way, it'll be amenable to using crypto tools to privatize the proof. So the first observation we make is that every SCT on the log and every log entry has a timestamp associated with it. And we're going to make the assumption that the timestamps that we use are in order. This is not something that's required in the CT specification right now, but it's intuitively it makes sense because these logs are append only. So later entries will always come after earlier entries. So once you have all of the timestamps in order and you have an SCT that's missing, you can naturally find where it should have been in the log because it'll fall in between two timestamps that are adjacent to each other. And once you have this information, we realize that all we need to really prove is that we have some SCT whose timestamp falls in between the timestamps of two log entries that are next to each other. And the reason this proves that the SCT is not in the log is because if this SCT corresponded to something that was in the log, then there's no way that these two log entries could be next to each other, because that SCT would be in between them. So this is what we want to prove. We want to be able to prove to Google that we have an SCT whose timestamp falls in between the timestamps of two log entries that are actually in the log. So we need to think about how we can do this privately. So there's a number of crypto tools that come to bear in solving this. The first one is an additively homomorphic commitment. So I talked about a commitment in the previous problem. So the way that an additively homomorphic commitment works is you get the same properties you had before, except you have this cool additional ability to do addition underneath the commitment. So you commit to a value 1, you commit to a value 2, and you have this power to compute the sum of these, value 3, without learning what value 1 was, without learning what value 2 was, and without learning what their sum is. So it's kind of cool that you can do things like this. Another thing that we're going to use is called a zero-knowledge proof. And zero-knowledge proofs allow us to kind of prove knowledge about commitments without revealing additional information about what the commitments are. So if we have a commitment to value A and we have a commitment to value B, we can prove that these are commitments to the same thing without revealing any additional information about them. Likewise, we can show that if a commitment is a commitment to a number, we can show that it falls in some range without revealing what it actually is or anything other than the fact that it falls in this range. One thing that's a little bit more fancy is that if we have commitments to some value and a signature to that value, there are a few signature schemes that have this nifty property where you can actually verify the commitment, verify the signature underneath the commitment. So even though you have commitments to two values, like a priori you know nothing about what these are commitments to, these signature schemes give you the power to prove that you have a signature and the value that it's a signature on without revealing any additional information about what is being signed. So we're going to use these to kind of convert the intuition we had in the previous slide into a cryptographic proof that doesn't leak anything about the missing SCT. So the idea is going to be we want to prove that we have an SCT in between whose timestamp falls in between these two log entries. And the way we're going to do it is we want to prove that we have these relationships that match with values that come from the log. So we want to show we have a log entry whose index is 1 off from another entry, and that the timestamps of these two entries have this SCT's timestamp in the middle. So the natural thing to do, if we have commitments and we want to hide what we're sending over, well, we'll commit to everything. So all the values we use will be commitments instead of the actual values. And then I talked about the zero-knowledge proofs we have that we can use to show kind of relationships among the commitments. So we'll do zero-knowledge proofs of the relationships that we want to have hold and send them over. So once we do this, we would be set. We've proven that we have these values that satisfy the necessary relationships. But the problem here is that this only works if we assume that the browser is always honest. Because if there were some malicious browser that had kind of been hacked to try to give a fake proof, it could currently get away with it in the scheme as I've described. And the reason for this is we have no mechanism to show that the values we're using in our proof actually corresponds to what came from the log. So if we had some browser that was malicious, it could just make up numbers that fit the conditions that we want and send over the proof, and Google would be none the wiser. It wouldn't know if it was looking at a legitimate proof or if it was looking at a bunch of just numbers that happen to satisfy the relationships we need. So what we're going to do to show that we have values that actually come from the log is we're going to use some of these cool signatures that I talked about on the previous slide in a kind of clever way. So what we want to do is that we want to show that we have an index and a timestamp that come from the same log entry. And I should mention that it's not only enough to show that all the numbers we use are from the log, because if we could show that, there's still this possibility for a kind of a mix and match attack where you pick two indexes in the log that are next to each other, and then you pick the timestamps from 3 other things in the log that happen to have an SCT in between them. So you need to make sure that the index value that you use and the timestamp value you use actually come from the same log entry. So the way that we do this is we want to show that we have an index and a timestamp that correspond to the same log entry. And what we're going to use as an additional tool is 3 signatures from the log. So every log entry is going to have next to it three signatures. One of them is going to be to the hash of that log entry. One is going to be to the hash with the timestamp added to it, and one with the hash with the index added to it. And when we have those 3 signatures, and we have these 2 values we want to get, we also are going to use the hash of the log entry itself. And the prover is going to send commitments to all of these values over to Google. So prior to sending over the proof that I showed on the previous slide, we're going to send over commitments to these 6 values. And once Google has these values, because the commitments we used were additively homomorphic, it's going to have the power to add them up so that it can get commitments to 3 values that correspond to the 3 values for which we have signatures. And once we have these things, we can verify the signatures underneath the commitments. And now, once we've done this, we know that the values for the index and the timestamps that we've used correspond to values that actually came from the log, because we have signatures from the log. But because everything is under a commitment, we don't actually learn what the values are that we're using. We don't learn what the log has signed. So we now have private versions of the index and the timestamp that we know verifiably come from the log. And once we have this, the proof from the previous slide can go through because you know that the numbers you're using are actually legitimate and not just made up. So I wanted to give you some performance numbers for our implementation of this. The main thing to note from this slide is that the offline costs, so these are the costs that go into like the amount of bloat in log entries and SCTs from implementing our scheme, is very, very small. It's on the order of bytes. So the real cost comes online when you want to generate these proofs and send them over, but this is something that happens only in the exceptional case that a log is caught cheating. So this is kind of a very low overhead scheme to put in. So all I wanted to say is that CT is this cool new part of the web infrastructure that's going to be standard later this year. And that although it solves this problem of rogue CAs and compromised CAs really well, it opens up new privacy concerns. And so I've presented a couple of privacy-preserving solutions for some problems that come out of CT. So I'll be happy to take any questions you might have.
I'm sorry, I may have missed, right here. Sorry. So you mentioned about the incident that happened where it was maliciously redirected to another fake CA and it issued a certificate, right? So with the log, how do you prevent similar kinds of malicious, redirecting to a log or, providing back log entries which are not valid but look valid?
Yeah, so the way that it works is that your browser is going to be preloaded with like a list of logs that are the trusted logs. And it's a sort of trust but verify system. So when your browser receives a signed promise from the log, it takes it on faith that this is legitimate. And then later it goes and it looks at the log and it checks. So if the log is caught cheating, you can kind of catch after the fact that it had been cheating. But the reason you can't be redirected to like a fake log is because the set of trusted logs is known from the beginning. So if someone tries to pass off some other log, it would have to steal the kind of the private information of the logs, which is a much bigger attack. Yeah.
So self-signed certificates are a royal pain today. Is this going to make it any worse?
You mean like if you want to use a self-signed certificate? Well, I mean, there's kind of a legitimate reason why we might want to distrust self-signed certificates, because we don't have any like root of trust for them. So I think that's...
You're not going to make it any worse, though, this new policy that Google's going to have in October. It's bad enough, but it won't be worse.
Yeah. Will they even be allowed? Oh, I guess if you have a self-signed certificate, it'll also have to show up in the log. So there's kind of higher barriers.
But each log has a list of roots that it trusts, that it will accept certificates from. So all the logs I know of won't accept the self-signed cert to put into the log.
Yeah.
I have a question. On your first idea about commits, I think you talked about the customer, the domain owner, creating the commit and sending it to the CA. Is there any way the CA is able to do that instead so that we don't have to put the burden of doing some computation on each customer?
Yeah, I mean, it's about the same if the CA does it versus if the customer does it.
I mean, there's no concerns about privacy or trust or whatever.
I mean, it's just a matter of if you trust the CA to do it, then you can do it. So if you don't trust your CA, then the CA could potentially create a commitment to something else from what you wanted, and you wouldn't know. So that's one way that you could kind of get in trouble. But if you trust your CA to do its job correctly, then you're fine to have the CA do this step instead.
Last question. Here we have a microphone there. Go ahead.
I guess my question is if somebody is able to create a fake certificate, that basically doesn't that mean that they have compromised the private key of the CA that issued the certificate? So the idea of creating these commits, which kind of look like a token, is that now you're transferring the trust from that private key that issued the certificate to the key that, I guess, created the token. So isn't that basically the same problem? You still lost your trust in the private key that issued the certificate. So how is this different? I don't understand.
You're referring to the CT scheme or to the
To the CT scheme, right? I mean, it looks like something that is signed by some secret. Am I mistaken?
So you're saying that why are we not just pushing off this problem of trust to the logs instead of?
Well, it sounds like if I lost my trust in the private key that issued the certificate.
Yeah.
Why would I now trust the same CA or the same fake CA that is creating the tokens and the logs? Because I don't have any trust in that private key anyway.
So I mean, I don't think the CA and the log are not necessarily the same parties. They're running different keys. So you could the idea is that this log kind of lets you look at the activities of the CAs, and that's how you verify that the CAs, you can catch a CA that's gone bad, and then your browser is able to verify that the log is not cheating. So we kind of close the loop where we don't need a trusted third party anymore. I'm not sure if that answers your question. Yeah. We can talk about it after too.
All right, why don't we call it there? So thank you again for the talk.